Hello everyone. So in the last lecture we have discussed about phase transformation, shock wave induced phase transformation, and we have seen that relation between this phase transformation and Rankine-Hugenoid curves. So today we will continue these discussions and we will see some of the examples of the materials that undergoes shock wave induced phase transformation. So there are some common example of shock wave induced phase transformation. One is already mentioned about this alpha iron transformation to epsilon iron. So as you know, this first one is BCC, and then after transformation it will be hexagonal closed pack structure. And the second example is graphite to diamond phase transformation under shock loading, graphite to diamond. So we will first talk about the number one phase transformation, that is alpha iron to epsilon iron. In a previous class we already have shown that this phase diagram, unary phase diagram of iron. So this is, unary phase diagram of iron, Fe. So these phase diagram is under y axis temperature axis and x axis is pressure axis. Pressure is in terms of gigapascal and temperature is in terms of Kelvin. So where this phase is the gaseous phase, this is the liquid phase, and here in this phase the small area, small region will be delta phase, delta iron, which is BCC, and this area is gamma iron, this is gamma phase, that is FCC, and at the lower temperature it has BCC crystal structure, that is alpha phase, and then epsilon phase with hexagonal closed pack structure at very high pressure. So this pressure is 10 gigapascal, 20 gigapascal here, and then temperature is like 1000 Kelvin, 2000 Kelvin, 3000 Kelvin. So and as you know, I think all of you know about it, about the phase diagrams and about Gibbs phase rule. You have, I'm sure that you have studied in your undergraduate courses of basic material science. Gibbs phase rule, which is equal to F C minus P plus 2. F is the degrees of freedom, number of degrees of freedom. So I will not write the number word here because due to less space here, but you please understand that these all are numbers of degrees of freedom. Then C is numbers of components. Here I can write number of components in the system, and then P is number of phases, and then the 2 denotes actually temperature and pressure. If we have at fixed pressure or at constant pressure, the Gibbs phase rule will be C minus P plus 1. As you know, some other phase diagrams at constant pressure, so you have seen that I'll draw in the right hand side. So at constant pressure you have in the y axis temperature and x axis is percentage composition. So this is these type of diagrams, phase diagrams, are generally drawn at constant pressure, and for that this Gibbs phase rule will be F equal to C minus P plus 1. So here I want to just remind you the term component means for example, if we have a water and ice system, so there we have a single component because water and ice both are H2O, and also but in there are two phases, one is solid phase and one is liquid phase. So so you should understand the difference between components and phases. So in this case, in this diagram, we are calling it as a unary phase diagram because it has one component only. What is the component? Component is iron. One component, that is iron. Okay, so I will draw a line so that this diagram looks nicer. So what we want to discuss now is we will discuss how this phase rule is obeyed in these phase diagram. So first we will see the single phase region. This is a single phase region, and where the only liquid exists, and here is another single phase region where we have only gamma phase exists. Similarly, in this case, in a gas in this region, and then alpha is in BCC, that region, and epsilon D, all are single phase region. But for our this illustration, we will only show only two single phase regions. So these single phase regions, I light phase regions. So our F is equal to number of phases 1, number of component is 1 and number of phase is 1, because we have only liquid phase or only gamma phase. So you should be you should be aware of that, although I am having two arrows here, but we are talking separately of liquid phase and gamma phase. So we can show for each single phase region separately this Gibbs phase rule separately. So this will give us F equal to 2, and similarly if we talk about these two phase regions, so two phase regions on these lines, suppose this line can have both gas and liquid phases, and this line can have both liquid and gamma phases. So these lines are two phase regions. Two phase regions. So F is equal to component is 1, phases are 2. So this will give us degrees of freedom equal to 1. So we will see what is that degrees of freedom, and before that, so we want to show you these triple points where three lines meet each other, and these are a region of 3 phases. So in this case, suppose these triple point, there are 3 phases will coexist. So one is liquid, one is delta phase, and one is gamma phase. Similarly, in this triple point, so there will be 3 phases. First one is the gamma phase, and then epsilon phase and alpha phase. So these triple points, I will draw the arrow like this, and these triple points, this has 3 phase region, and that points are called triple points. 3 lines meet each other, and for that points, for those points it will be only one component iron, and then 3 phases plus 2, that gives us the degrees of freedom equal to 0. So now try to understand this. In the single phase region, F is equal to 2, that means both pressure and temperatures are independent variables. In the single phase we got F equal to 2, so both pressure and temperature are independent variables. That means you can vary P and T inside these single phase regions, but for the two phase case, if you see here F is equal to 1, so that means only one variable is independent, only one independent variable, either T or P. So if you see on these lines, that means the two phase regions. So if you fix the pressure, then if you vary the pressure, you cannot vary the temperature, because temperature is fixed on those particular values of pressure. Similarly on the other way also, so these lines we can vary only one variable, other variable is automatically fixed. And for these 3 phase triple points, these are fixed points, we cannot change by varying pressure on temperature. So suppose for example this point is fixed at a particular pressure, let us say pressure is equal to close to 13 gigapascal, and also temperature is also fixed in this. So these are fixed points. So I am sure that you all studied these in your material science course, but just to remind you all this for our phase transformation chapter. Now this alpha to epsilon phase transformation was first reported by Bancroft and others in 1956. They first did that shock loading experiment, but later it was proved through static high pressure loading experiment as well, that at high pressures alpha phase can be transformed into epsilon phase. So and in this case, in this transformation, around 6% volume reduction happens. That means here our delta V is negative volume reduction. So from the unary phase diagram of the previous phase, what we got is that the pressure, transition pressure, if you see here in this line, the transition pressure decreases when with temperature, when you increase the temperature. So transition pressure decreases with increase in temperature. That actually what we found earlier, dP dt is smaller than 0, and these two from here we can say that if you remember the earlier discussions, the entropy will increase with transformation. So we can also see a pressure volume shock Hugenoid of this iron PV shock Hugenoid for iron. So you have volume, specific volume here, pressure in gigapascal. So it is 1.0, it starts from here and it goes like this. There will be discontinuity in slope, so it will vary like that, and this is in the loading case. And then in the unloading, this looks something like this. So this during loading, and this is, let's say, unloading. So during loading, this is, as you know, it's close to 13 gigapascal, where the discontinuity of slope occurs. And you can see that during unloading, the reverse transformation happens. So during unloading, reverse transformation happens. That means from epsilon to alpha, and it got completed at a pressure of 9.8 gigapascal. Here it is 9.8 gigapascal. So this, by the way, plot is from Duval and Graham. That reference we have earlier also quoted from Mark Mayer's book. So this is the reference. So you can see the discontinuity in slope at this point, as I told, nuity in slope. So from this shock Hugenoid curve, one can also determine the wave structure. We have discussed in the last lecture about the wave structure, two wave structures. The two waves travel simultaneously. So we will also probably discuss little later about these wave structures. So here this is a shock Hugenoid curve of iron. So this reverse transformation happens when you do unloading. So during loading, during shock loading, so alpha is totally transformed into epsilon phase. However, some residual transformation product left out. So although I wrote that it got totally transformed, but still some of the residual that transformation product left out, and so that's why the hardness, if you see hardness profile, so this is a micro hardness profile, hardness RA, Rockwell hardness, with depth. Depth means actually this is a test done by Mayer's group. So this Mayer's and others in 1980. So what they did is they obtained this plot by detonating plastic explosive on steel. The plot looks something like this. So depth is from the surface. So if you see, this is around 4 millimeter, and if you go 30, 60, 90 millimeter below, so and this hardness number is around 60 at maximum, and then reduces, let's say 40 here, 20 here. So what happens, you can imagine that during the detonation with help of a plastic explosive, the steel block after the passage of that shock loading will be very hard at the surface, that is up to 4 millimeter from the surface. So that means at the surface, this region, so pressure will be very high, P exceeds 13 gigapascal. That's why transformation happens, transformed, that region is transformed, and that's why hardness is very high, and the other region is not transformed, the other part, this side of that region untransformed. This is untransformed. So you can see that hardness can go up to very high. This is RA number 60 because of this transformation. Oh, sorry. So what I wrote here is loading. That is correct, that for during that is correct, that during loading alpha phase totally transform to epsilon, but what we talked about here is about the residual transformation product. So that actually we should have written that this is actually about reverse loading. It is about reverse loading from epsilon to alpha. So that's what we discussed in this point, because as I told you, the residual transformation product, that means the transformation product here is epsilon, because we got epsilon here from alpha to epsilon, and this is the transformation product. And so residual transformation product means some part of the epsilon will be left out, will not be converted to alpha. So that's what this residual transformation product means. And also in optical micrograph, you can see that optical micrograph, you can differentiate the two region, transformed and untransformed region. So the transformed region will look darker, and then the untransformed will be lighter in appearance. So we were discussing about shock induced transformation of iron from gamma iron to epsilon iron. So now again we will discuss another phase transformation, example of a phase transformation, shock induced phase transformation, that is graphite to diamond. So graphite to diamond. So this transformation we can retain after passage of the shock wave. So we can retain it, can be retained after the shock loading or the passage of the shock wave. Shock loading. So before going to the details, we will see how the unary phase diagram of carbon looks like. So unary phase diagram, if we have pressure in gigapascal in y axis, and if we have the temperature in Kelvin in x axis. So suppose we are writing in 2 gigapascal and 6000. So the phase diagram looks something like this. So here in this region at high pressure we have diamond as stable state, and then in this region we have graphite at low pressure, graphite, and then at high temperature we will find it as liquid state. Now here we can see that this in between diamond and graphite, so diamond and metastable graphite stays. So diamond and metastable graphite, and basically the diamond region is if we see, so these regions even above this line or mostly, and even some below this line also we can have diamond. This is what we have drawn is unary phase diagram, that is unary means one component, the only one component is carbon, unary phase diagram of carbon, this diagram. And the first researcher to report this graphite to diamond using shock loading, the transformation using shock loading was reported first by D. Curley and Zemison. These were the first person. They reported in 1961 that shock induced phase transformation of graphite to diamond. So diamond, if you see, it starts at a low pressure. Even this region, as you know, this diamond from graphite to diamond at a lower temperature, it can start as early as 2.3 gigapascal, start forming diamond. Okay. So these phase transformation, the result is results a very small grains, and also the small particles which are polycrystalline. That means the particles are also small size, which are polycrystalline, and even one grain also has a small size due to a limited time available to, for growth. So due to limited time available for growth, diamond crystals are crystals are very small. Dipole crystals produced by shock loading. DuPont company used to produce diamond using this method. So they use this method as a commercial method that means using shock loading. In these methods rapid cooling is required. To avoid graphitization. So that means it can be again convert into graphite. So to avoid that the rapid cooling is required, and sometimes the mixing copper with graphite helps in quenching. So copper as a quenching medium. And this graphite diamond transformation, this transformation is a martensitic transformation. Martensitic, that means it is diffusionless transformation, and the diamond produces hexagonal in crystal structure, has hexagonal structure, not cubic. As you know, FCC, it has FCC lattice with diamond cubic actually structure. That is, the crystal structure is called diamond cubic, and it has as an FCC lattice. This is a usual one, but in this case it is not cubic. This is hexagonal structure. With help of shock loading, whatever we produce, that has a hexagonal structure. As we already mentioned, that the particles of diamond produced with this method are polycrystalline. So they have even particle size even are probably less than 100 micrometer, and these grains, one single grain, let's say single grain has a single grain, or you can call it a crystal, has even less than 100 angstrom diameter. And applications, if you are concerned about the application of these small particles, these diamond particles are used as polishing agents. Used as polishing agent. We will now talk more about these two-wave structures. So we will see the most of these discussions were taken from one another reference, that is Oscar Bruno, Dimitri Weinbelt, they are from Caltech, California Institute of Technology. So that is a technical report published in June 2000. So that is titled as Shock Induced Martensitic Phase Transitions, Critical Stresses and Two-Wave Structures that solve the Riemann problem. So, so this is the reference we will be discussing. Suppose a typical experiment, we know that we to produce a shock wave is we have a flyer plate, that's we can call it the projectile. This is a projectile and the target is this one target, and when you get the particle velocity history, so we get the UP history, particle velocity histories obtained by Weiser. We talked about this, that is velocity interferometer system for any reflector. So, on the back surface of the target the UP histories can be obtained by this using this technique, and when the projectile will hit the target, so we will see what kind of shock wave will be propagated. So, this is what we are discussing is related to shock induced phase transformation. So, this is a planar projectile, by the way, this is planar projectile, and let us say it is hitting the free surface of the target. Let us say you can say that a flat target is, let us say, flat slab. When it hits, suppose the projectile hits the target, so this surface, this actually not surface, this is interface, this interface is, we will call it as impact interface, or simply we can call, for our discussions we can call it as only interface even. So, in this example, so the ratio of the lateral to the longitudinal dimension is chosen such that, so the lateral dimension is high such that all the measurements are such that all the measurements are done are completed before the release wave arrive from the lateral surface of the target. That means when you are hitting the target, so the shock wave will propagate in this direction, but there will be some release wave from the surface, lateral surface. So, these relief waves we do not want to any interaction from these release waves. So, that is why what we assume is that the lateral dimension is very high, so that the release waves cannot interact with the primary shock wave. So, that is the assumption here, and that assumptions mean that the lateral dimensions should be infinite, and wave motion is one dimensional. One dimensional means normal to the interface, normal to impact interface, or I would write just interface. After this impact, this interface velocity, that interface velocity after the impact, rises from 0 to a certain value. So, value is, let us say, Vi at in a very small time, let us assume t star. So, small time t star. So, this is the value Vi this is the interface velocity. It's this is a very small time, but it's non-zero, not zero, not equal to 0. So, that means the rise of this interface velocity is very quick. So, it is in a very small time it rises to velocity Vi. So, this impact interface, I will just write interface, will have a that undergoes acceleration. That acceleration we would write x double t acceleration, which is positive acceleration, and after a small time interval t star. So, the target boundary travels at a constant speed, and the target boundary means the free surface or the impact interface. So, that means that Vi is equal to, you have this. So, we can write it that way. For we have let us say 3 cases here. If Vi is small, or we can call sufficiently small, then this means sigma is smaller than a critical value, sigma critical, throughout the target, and that means no phase transformation, transition or transformation. So, what this critical means? So, if it is below the critical, the stress is below the critical limit, then no phase transformation, and that is true for Vi for less than a some value, that is Vi V critical, you can see. So, if Vi is equal to V critical, then sigma is equal to sigma critical. So, sigma critical at a single surface. So, it is that is the impact interface, but although this stress is sigma has the value the critical value. So, higher value of sigma, that means that is sigma critical, higher than the sigma critical, will not be will not occur at will not occur at any time within the target. So, this means also that the no phase transformation. This means that no phase transformation like the earlier case. And number 3 case is if Vi is slightly even higher than the critical the value, if Vi is higher than, even if it is slightly higher than V critical, what will happen is the shock wave will result in a growing layer with a material that has sigma is greater than sigma critical behind the shock front, so which is close to the impact interface and close to the interface. Interface always means the impact interface here. So, in this case the impact interface acceleration will induce volume decreasing phase transformations. So, what will happen is there will be a growing layer with sigma critical, and that means it will favor a phase transformation, that is, as we know, it is a volume decreasing phase transformation, delta V smaller than 0. So, now we see these three cases. So, first one, if the Vi is small, there will be no phase transformation toward the target. So, what will happen is here in this case a single regular shock front will travel, single we would say regular. So, there is no phase transformation, regular shock front. In the second case also, because there is no phase transformation, so because of that, in this case also there will be a single shock wave structure like the first case, single shock wave structure. But in the third case, there are this case is different than the earlier two cases. So, it will have two wave structure, two wave structure. Now, we will see how it has the two wave. So, we will explain these plots later, but before that, what we want to draw this again with the projectile and the target. So, what will happen is in the third case, when sigma is sigma critical, so what will happen is this is the projectile. So, we will now talk about the target only. So, first the entire the target has a austenitic structure, we call austenite, austenitic structure. Then after in the third case, when the sigma will be sigma critical and this velocity Vi has a slightly higher value than and V critical. So, in this case you want to see again. So, Vi has a the value has higher than the V critical, and then sigma is higher than the sigma critical. So, what will happen is this is the impact interface, right. So, this is the impact interface. The material close to this impact interface will be transformed to martensite. So, and then earlier it was austenite. So, we will remove this. So, it is now transformed to martensite, and at that time the shock front will be somewhere here. So, this is our shock front. So, here what is happening is the entire this zone we have both austenite, still we have austenite, and then this is the shock front, the first or regular shock front. But here we will have one more shock wave. So, that is the transition front or the transformation front, because this is the interface, of martensite and austenite. So, that interface will also be going forward in these direction. So, this is the first shock front, and that is transition, we would say transition shock front. So, there will be two shock front here. So, that is why it is called as two shock wave structure. So, first front is this one, and in this region, first region, actually I would write 1, 2 and 3. So, in the first region, sigma is equal to 0, because the shock front, the first shock front has not even reached yet, and the number 2 region that has a, let us say sigma equal to sigma critical, but but still the transformation has not occurred, as you can see in the earlier slide. So, number 3 region have sigma which is greater than sigma critical and transformation occurred. So, that is the austenite structure transformed to martensite, which is we told that is a diffusionless transformation. So, that martensite and austenite interface is also another shock front. Now, following the first or the primary shock front, but in case if the velocity is very high, speed of the transformation shock front. So, these transformation or transition shock front, you can take it as same. So, transition shock front, the speed will depend on the Vi, you know, that impact interface velocity. If Vi is very high, Vi is high, so what will happen, that that will have a very high transition shock wave front speed. This we can write as U transition shock wave. So, U, or for the first shock front we can write U velocity, U shock wave, and here we can write U transition shock wave. So, the speed of the transition front. So, this speed as it is increases, so what will happen, if Vi is very high, there will be only transition shock front. That can be shown in this diagram. So, this plot is the reference is Erskine and Nellis. Erskine and Nellis. I actually forgot the year of the publication, but anyways, so this shows in the y axis it is interface velocity, that is written in kilometer per second, and in x axis it is time, microsecond. It is actually these times are showing very close to 0. This is actually, it is just staggered. You can see, you can think that this is a very small time. It's close to 0. That's a positive, not 0. It should be positive actually, although it is shown as staggered like this. So, these 4 curves are for 4 different impact velocities. So, I would write impact velocity as V. So, suppose for this curve is V equal to 2.6 kilometer per second, that is a very high velocity, and the other one is second one is 3.12 kilometer per second, and the third one is 3.47 kilometer per second, and the last one is 3.9 kilometer per second. So, if you see in the first one 2.6 kilometer per second, you can see there are some change of velocity after some time. So, and also similarly in the second case also you can see a similar structure, although it's the change happened in at a lower time, and similarly in the third one also you can see a change, but then the fourth one looks little different. The changes happen at the last, and this is actually some fluctuation, but there you can assume that there is no change, like, so you can assume it like this. So, this means that if you have two velocity, interface velocity, one is corresponds to, let us say below 1 kilometer per second, another one is corresponds to below 2 kilometer per second, or similarly for the other two 3.12 kilometer per second impact velocity and 3.47 kilometer per second the impact velocity. So, just to again remind you, these velocities what I have written 2.6 or 3.1 to 3.47, these are impact velocities, and then interface velocities, impact interface velocities that can be produced from this is in the y axis. So, now what is happening, if you are seeing these change of velocities, like we can see very prominently in the first case. So, that means it has a two wave structure, but in case of 3.9 kilometer per second impact velocity, it has a single wave structure. So, that I have already told, only transition shock front, single wave structure. So, if you want to again see the earlier slide. So, when the Vi is very small, then it has a single regular shock front, and then Vi equal to V critical also you have a single shock wave structure. But when Vy is equal to greater than V critical, and that will create a stress that is actually this sigma is the compressive normal stress we are talking about. I forgot to mention that. I hope that was understood, compressive normal stress we are talking about. So now this, if it is sigma is greater than sigma critical, so that will give us a two wave structure. But if the velocity, impact velocity is very high, then what will happen is the interface velocity is high, and that will give that the transition shock front will dominate, and that will again eventually will get a single wave structure, that is only the transition shock front. That is all for today. So, we have discussed about different phase transformation. We have discussed about phase transformation of iron, and then we discussed about carbon phase transformation from graphite to diamond, and then we even discussed about two wave phase structure, two wave shock wave structure, that is we even discussed in an earlier class as well. So, we will continue this discussion on shock wave a little bit on the next lecture, and then after that we will go forward to some other chapter. So, thank you.